Section 2.2, the derivative as a function. So in this section, I'm going to give you notation and further concepts involving the derivative. So again, I'll be a little bit more precise even than I was in the last section on the concept of a derivative. And I'll also give you the definition of, well, the idea of a derivative as a function. So since it's defined at every point, since it's defined at points, I can think of a derivative as a function. So let f prime of x equal the limit as h approaches 0 of f of x plus h minus f of x, all divided by h. So let me give you some notation. F prime of x, I can write it as y prime. So this is the prime notation, which is, let's see, the prime notation was the French. So I think next, the capital D notation, the operator notation. So d f of x, or d sub x of f of x. And I believe that was mostly Germanic notation. And the little dot notation, where you put a y with a little dot above it. And so the flexion notation, that was the British notation. I'll be using, well, depending on the problem, I'll be using one of these notations, or I'll be using Leibniz notation, German, which is a nice notation. So I particularly like Leibniz notation. So dy over dx, or df over dx, or dx, d over dx, f of x. Now, if I'm going to be doing it at a particular point, then for Leibniz notation, I'll write dy over dx at a equals, well, dy over dx, where I'm evaluating when x equal a. Notice you take the derivative first, and then you evaluate. So this is a little bit of a bad notation, because it looks like you're taking the derivative of y at a, which is, you're not. You're taking the derivative and then evaluating when x equal a. A function f is differentiable at x equal a if f prime of a exists. If f is differentiable, it is differentiable on the open interval ab, or on the open interval from a to infinity, from negative infinity to a, or negative infinity to positive infinity, if it is differentiable at every number in the open interval. Now, what happens if there are endpoints, such as a half open, half closed interval or a closed interval? What do you do with those endpoints? Well, so that's the question. What do you do if you try to include the endpoint A, or you're trying to include the endpoint B? Well, I have to talk about, just like what we had to do with continuity, well, we had to talk about right and left-sided limits. I'm going to have to talk about a right-sided derivative. Same concept as before. It's just that it involves a right-sided limit. So the right-sided derivative of f at a is the right-sided limit as h approaches 0 of f of a plus h minus f of a, all divided by h. Similarly, let's talk about the left-sided derivative, where I try to include a right-sided endpoint. So everything is nicely defined on the left side. It's not defined on the right side. And I want to include this right-sided endpoint. So just like what we did with limits, with continuity, I had to talk about a left-sided, to be continuous from the left. Well, I'll talk about a left-sided derivative. The left-sided derivative of f at b is a limit as h approaches 0 from the left of f of b plus h minus f of b all divided by h. So let's talk about a derivative defined on a closed interval. So both at a and at b. So f is differentiable on the closed interval ab if f prime exists for all x in the open interval ab, and if the right-sided limit exists at a and the left-sided derivative exists at b. Theorem. If f is differentiable at a, then f is continuous at a. So if you have a function that has some sort of derivative at a, meaning it looks like a line at a, then it's continuous at a. Because, well, if it looks like a line at a, then you can draw it without having to lift your pen off the paper. So if f is differentiable at a, then f is continuous at a, but not vice versa. Meaning that if a function is continuous at a, it's not necessarily differentiable at a. And we'll see that in a second. So let's suppose that f is differentiable at a, and I want to show that it's continuous at a. Since f is differentiable at a, there exists a number, well, let's call it f prime at a, and it's some real number, so that f prime of a is equal to limit as h approaches 0 of f of a plus h minus f of a over h. That's just the definition of what it means to be differentiable at a. So that means there exists a delta 1 greater than 0, such that if h in absolute value is between 0 and delta 1, then f of a plus h minus f of a over h minus f prime at a in absolute value is less than 1. Let g of h equal, well, the difference quotient, so long as I'm not dividing by 0. And if h is equal to 0, then let it be the derivative. Let it be this limit. And so, meaning I'm going to somehow define a continuous function where for this difference quotient. So let g of h equal f of a plus h minus f of a over h if h is not equal to 0. And let it equal f prime at a if h is equal to 0. So h in absolute value being less than delta 1 implies that g of h minus f prime at a in absolute value is less than 1. Certainly that's true because g is equal to this quotient if h is not equal to 0. And so from here, I have that this absolute value of this is less than 1. And if h were equal to 0, That's why I don't need a 0 here. If h were equal to 0, well, then g is just equal to f prime. F prime minus f prime is 0, which is less than 1. So no matter what, if h in absolute value is less than delta 1, then g of h minus f prime at a in absolute value is less than 1. So given epsilon greater than 0, let delta 2 equal epsilon over 1 plus absolute value of f at a. Well, this is greater than or equal to 0. Add 1 to it. It's greater than 0, so I'm never dividing by 0. Positive divided by positive is positive. So this is greater than 0. So let delta be the minimum of delta 1 and delta 2. This delta 1, so this holds, and this delta 2, it satisfies this. So if h in absolute value is less than delta, then h in absolute value is less than, by this, epsilon over 1 plus absolute value of f prime at a. And so the absolute value, so f of a plus h minus f of a in absolute value is equal to, well, the absolute value of g of h times h. If h is not 0, then multiplying this by h, this cancels. And so this is just equal to h times this. Oh, there it is. And so this is just equal to h times g. If h is equal to 0, well, then 0 times anything. Oh, by the way, this is defined at h. So 0 times this quantity, whatever it is, it exists. 0 times this quantity is 0. So I get if h is 0, this is 0. And if h is 0, then f of a plus, well, a plus h is just a. So f of a plus h minus f of a is 0. So these are equal. So therefore, no matter what, this is a true statement. Now, by the properties of absolute value, this is the same as the absolute value of g of h times the absolute value of h. I can add and subtract f prime at a. That's not doing anything. So this is equal to f of g of h minus f prime at a plus f prime at a in absolute value times the absolute value of h. By the triangle inequality, I can just take the absolute values of each of these. And so this is less than or equal to absolute value of g of x, the absolute value of g of h minus f prime at a plus the absolute value of f prime at a all times absolute value of h. Well, I have a bound on this guy. This is going to be less than 1. So by this, I have that this is less than 1. Sorry, this is less than 1. And while this is still f prime, the absolute value of f prime at 1. Next, I have that a bound, oh, right here. I have a bound here on this guy. This is because of delta 2. These cancel. So what I have remaining is epsilon. And so that says that this is less than epsilon for all epsilon. Oh, so this is actually saying that the limit as h approaches 0 of f of a plus h is equal to f of a, which we know by, so we know that the limit as h approaches 0 of f of a plus h minus f of a is 0. But we've proven back in section 1.7 that this is equivalent to limit as h approaches 0 of f of a plus h equaling f of a. But this says that f is continuous, and this is equivalent to the limit as, oh, maybe I should have said that this also. This is equivalent to the limit as x approaches a of f of x equaling f of a. That's another one of the equivalences that we gave back in section 1.7. But then this says that f is continuous at a. And so we're done. That's what we wanted to show. So if f is differentiable at a, then it's continuous at a. So differentiability at a implies continuity at a. But the question is, well, is continuity the same as differentiability? Meaning, can I go in the other direction? If f is continuous at a, is it differentiable at a? And the answer is no. Let's give a counterexample. The counterexample is probably going to be the absolute value. Yeah, the absolute value. So let's give a counterexample to that. So note the following, that if y equals the absolute value of x, then this function here is continuous at the origin. The limit as x approaches a of the absolute value is 0. If I look at, not that you really needed to, the limit as x approaches a from the right side, well, you're going to get, as x approaches 0 from the right side, I have that the limit as x approaches 0 from the right side of the absolute value of x is just the limit as x approaches 0 from the right side of x, which is 0. Similarly, let's approach 0 from the left side. So the limit as x approaches 0 from the left side of the absolute value, well, the absolute value for x is less than 0 is just equal to minus x. So this is equal to the limit as x approaches 0 from the left side of negative x, which again is just 0. Therefore, limit as x approaches 0 of the absolute value of x is 0. Therefore, the absolute value of x is continuous at 0. Let's check if it's differentiable at 0. Well, to find if it's differentiable at 0, let me look at the right and left sided limits, the right and left sided derivatives. And so let's look at the right sided derivative. So the right sided derivative of f at 0 is equal to the right sided limit as h approaches 0 of f of 0 plus h minus f of 0 all divided by h. So this is equal to the right-sided limit as h approaches 0 of the absolute value of h minus, well, the absolute value is 0, which is 0 over h. If h is greater than 0, then the absolute value of h is just h. So this is equal to the limit, the right-sided limit, as h approaches 0 of h over h. well, h divided by h is just 1. So this is equal to the right-sided limit as h approaches 0 of 1, which is just equal to 1. So the right-sided derivative of f at 0 is 1. We can see that because the slope on the right side of 0, it looks like this line, which has a slope of positive 1. Let's look at the left-sided derivative. So the left-sided derivative of f at 0 is the left-sided limit as h approaches 0, f of 0 plus h minus f of 0 divided by h, which is the left-sided limit as h approaches 0 of the absolute value of h minus the absolute value of 0 over h. Absolute value of 0 is 0. If h is less than 0, then the absolute value of h is negative h. So this is equal to the limit, the left-sided limit, as h approaches 0, of negative h over h. Of negative h over h is just negative 1. So this is equal to the left-sided limit as h approaches 0 of negative 1, which is equal to negative 1. So you notice that if I look to the left of 0, it looks like a line of slope negative 1. So the right and left-sided limits of f at 0 are not equal. Therefore, the two-sided derivative at 0 doesn't exist. Therefore, f is not differentiable at 0. And so, f being continuous at a does not imply that f is differentiable at a. Is that clear? This is a very important concept, that if you are continuous at a, you are not necessarily differentiable at a. But if you are differentiable at a, it is you must be continuous at a. So if you're differentiable, then you are continuous. But if you are continuous, you may not necessarily be differentiable. Any questions about that? Okay, so let me look at how can I be not differentiable at A? So, well, one way is having a cusp. And so if you look at the graph of y equaling x to the 2/3, then the graph of that will look something like what I've just drawn here. And if you notice that the derivative here goes vertical, it looks like the tangent line is straight up and down. And so it has this like infinite slope. Actually, on this side, it goes to negative infinity. On this side, it has a positive infinity. So it has this slope here that's vertical. Well, this tangent line that's vertical. And so the slope is either plus or minus infinity, depending on if you're looking at a right or left-sided limit. And so if you have that the right and left-sided limits are plus or minus infinity, and that the right and left-sided limits are I said limits, I should say derivatives. So they are right and left-sided limits, but I'm talking in particular the derivative. If the right and left-sided derivatives are plus or minus infinity, and if the right and left-sided limits are not the same infinity, then we have a cusp here at A. And that's what it looks like. Next, I could have some sort of corner, like what I had from before when I took the absolute value. So if you look here, I have this sort of corner where the tangent line looks like two differing points, two differing lines. So if you look near x equal a, on one side it looks like a line, but on the other side it looks like a different line. So as you keep getting closer and closer to this point, it does not look like a line, it looks like, well, a corner. And so, actually that kind of was, I guess I was, that's what, this is supposed to be at A. I guess I shifted this over a little bit, but when I drew it. So suppose you have a corner at A, then F is not differentiable at A. So if you have any sort of corners here, then you're not differentiable at a corner. Also, well, we saw from before that in order for you to be differentiable, you must be continuous. So if you have some discontinuity at A, any of our discontinuities, it could be a jump discontinuity, it could be that you're not defined at A, that you have removable discontinuity, any sort of discontinuity at A, then we say, well, this is the reason you're not differentiable, because you have a discontinuity at A. Next, you could have a vertical tangent line. So if you look at your tangent line, it goes straight up and down, and the right-sided and left-sided derivatives are equal to the same. So if the right and left-sided limits, right and left-sided derivatives are equal to the same infinity, either plus or minus infinity, then we say it has a vertical tangent line. If they're equal to different infinities, then we say that it's a cusp. And those are really the classifications that we have for differing types of non-differentiability. Now, of course, there are lots of other types of ways that you can be not differentiable, but you can't draw them. So these are the types of discontinuities that I can draw. And so other discontinuities that can't be visualized. But these are the type of discontinuities that the types of non-different. Why do I keep saying non? Why do I say? Okay, these are the types of non-differentiabilities that I can draw. Please scratch out from your mind when I said when I said discontinuities, I meant non-differentiability. Okay. Let me give you some notation for higher derivatives. So first for the second derivative. So the second derivative is the derivative of the first derivative. And so the derivative of a first derivative is called the second derivative. And well, I can denote it by these little 2 primes. The derivative of the second derivative is called the third derivative. So some notations for the second derivative. I can put 2 primes here. I can do the d of x and put a superscript of 2 to say that it's the second derivative. This is the second derivative of f at x. This is the second derivative. So this is Leibniz notation. So why is Leibniz notation so strange? So let me sort of explain this notation. So this is the derivative. There. So this is the derivative of the derivative of y. So I have here, well, obviously there are two d's, so that's d squared y, and there's a dx and a dx, so this is dx squared. And now we're going to be lazy and forget the parentheses. And that's the notation. So the notation is we forgot to write the parentheses. It's just a notation. And so that's the weird sort of notation that we do, is we just sort of forget to write the parentheses. Okay, so that's that notation. Next, we have Newton's notation. We can do these two little flexions, these two little dots above it. Now, in general, and this is why I wrote it this way, when do I write this Newton's notation, this flexion notation? When I have x as a function of t, I write the derivative in this fashion. So if x is a function of t, and I want to find the derivative, I put a little dot above it. And so that's why I said x double dot. Next, third derivative. Well, the notation is y triple prime, or d sub x cubed at f, or Leibniz notation, d cubed y over dx cubed. So again, just like before, you just sort of don't write the parentheses. Now, problem with the prime notation is, well, if you have a lot of derivatives, it's hard to figure out what the heck's going on. So usually what we do is, when we have like more than 3, we then do it as a superscript. And so we usually do y, and then we do Roman numerals, lowercase Roman numerals. So y to the IV, and you put it in parentheses, these Roman numerals. Now, problem is as well, people don't know their Roman numerals past a few. So once you get past, so for 4, 5, 6, and 7, use this Roman numeral superscript. After that, we just use regular, numbers. So we go y to the 8. That means the 8 derivatives. You have to have a parenthesis. If you say y to the 8, then you think that that's y to the 8th power. Well, that does denote y to the 8th power. If you put a parenthesis around it, then that's the 8 derivatives of y. So this is 9 derivatives of y. So just keep taking, so that's the derivative of the 8th derivative of y, etc. Let me give you some notation so that I can give you an additional definition for the derivative, which will be very helpful in later courses. This will be the derivative that you will be using throughout most of your courses. Matter of fact, it's unlikely that you'll see any other derivatives ever in your lifetime, unless you're a specialized mathematician. So, little o notation and the definition of derivative. So, let's denote the limit as h approaches 0 of g of h over h equaling 0 by the fact that g of h is little o of h. So if G is little o of h, then this means that this limit of G over h goes to 0 as h approaches 0. So G goes to 0 even when I divide G by h. It still goes to 0 as h goes to 0. So it goes to 0 very fast. It goes to 0 faster than h goes to 0. So G goes to 0 faster than h goes to 0. Because if I divide G by h and let h go to 0, this ratio still goes to 0. So if I look here at the definition that we had from before of the limit, that the derivative is the limit of these difference quotients. The limit as h approaches 0 of f of a plus h minus f of a over h is equal to f prime at a. Well, that's the same as subtracting f prime of a from both sides of my equation using actually the equivalent forms for the limit. This is the same as the limit as h approaches 0 of f of a plus h minus f of a minus f prime at a times h, all divided by h equaling 0. But this, when I divide, so I have that this, when I divide by h, goes to 0 as h approaches 0. Oh, so this, when I divide by h, goes to 0 as h goes to 0, means that this quantity here is little o. And so this must be little o. Let me make some notation. Let's call this the change in f. So delta, usually in previous classes, you just called it delta y. And in this class, we usually call it delta y, but I'm going to use this notation. Let delta f sub a at h equal f at a plus h minus f of a. And so this, I'm going to call delta. And this, I'm going to call dA. So d f sub a at h will let this equal f prime time at a times h. This is something special. It's a particular type of function. And so let me give you the name of this function. We call L a linear transformation. Transformation is a very fancy word for function. So sometimes we call functions transformations. When functions are between two differing spaces, such as vector spaces, we call that function a transformation. Why? For historical reasons. So there's no good reason other than the fact that historically, people have called them transformations, or sometimes linear maps. So sometimes they call it a map. But again, they're just functions. So it's a fancy word, a fancy terminology for the word function. So we call L a linear transformation if L at AU plus BV is equal to ALU plus BLV. So let's see what this means for all numbers A and B. So these are numbers of your scalar field. And U and V are some points in your vector space. So let's do an example. Let L of x equal 3x. Then this is a linear transformation. And so L of AU plus BV, let's just plug in AU and BV, is just 3 AU plus BV. I can multiply the 3 inside the parentheses. And so this is just A of 3U plus B of 3V. But 3U is just L of U, and 3V is just L of V. So this is equal to A LU plus B LV. And that means that this is a linear transformation. So, unfortunately, in previous classes, pre-calculus, etc., especially in high school, they gave bad terminology. They would say y equal 3x plus 1 is a linear function. And actually, it's not a linear function. It's an affine function. It's an affine transformation. But I still call it a linear, a linear function, just because that's what they call it in high school. Okay, so whereas L of x equaling 3x plus 1 is not a linear transformation. It's not a linear function. So why? Well, let's check. Let's look at L of U plus V. Let's plug in U plus V here. And so we get 3U plus V plus 1. We'll apply 3 inside the parentheses. So I get 3U plus 3V plus 1. Okay, so let's look at L of U. Well, L of U is 3U plus 1. L of V is 3V plus 1. But you only have 1 here. You can't have the 1 for both this guy and for this guy. So this 1 here can only go to one of these, not to both of these guys. So L of U plus L of V is 3U plus 3V plus 2, not 1. So L of U plus V is not equal to LU plus LV. So unfortunately, linear functions from high school are not linear functions. They're not linear transformations. So actually, that's one of the reasons we call it linear transformation, so that you don't get confused with the terminology from high school where they say a linear function. And so we'll call it a linear transformation, so that linear, you don't think that, that a linear function is a linear transformation, because it's not. So let's go back to what we had from before. So the limit as h approaches 0 of f of a plus h minus f of a minus f prime at a times h over h equaling 0. This implies that, well, let's use that simplifying notation that we had. The limit as h approaches 0 of delta f sub a at h minus dA f sub a at h, all divided by h equaling 0. So now we have that this divided by h equaling 0 is 0 when h approaches 0. Therefore, this quantity here is little o. And so I have that delta f sub a at h minus d f sub a at h is little o of h. Let's bring this to the other side of my equation. So delta f sub a at h is equal to d f sub a at h plus little o of h. So now I can make this into my definition for the derivative. So this is really the definition of a derivative that is better than the definition I gave you earlier today, because it will be applicable in many more cases than the definition I gave you a few minutes ago. So, definition of the derivative. F is differentiable at A if there exists a linear transformation df sub A such that delta f sub A at H is equal to d f sub A at H plus little o of H. And so this implies that the limit as H approaches 0 of delta f sub A at H minus d f sub A at H over H is 0. So to determine f sub A at H, let's consider similar triangles from the following. So let's look here at this situation, and we'll figure out some similar triangles here. So suppose we have some function f, so y equal f of x, relative to some coordinate system. And suppose we have some tangent line to f at x equal a. Then let's take another point on the line and look at the secant line through a f of a plus h. The tangent line to y equal f of x at x equal a is the best linear approximation to y equaling f of x near x equal a, which has slope f prime at a. So best meaning little o. Linear approximation meaning linear transformation. So this here is the best linear approximation. So linear approximation, delta, best meaning little o. So this is the best linear approximation to f near x equal a. The tangent line to y equal f of x at x equal a, the best linear approximation to y equal f of x near x equal a, at a, we have the point a f of a. On the line, we also have the secant line. So at a plus h, this is f of a plus h. So we have some secant line here. We add to a h. This is the line that we want, whereas this secant line is the line that we obtained with our, okay? And so this here, well, let's do this one here, which I can do easier. So this distance here, this difference here is the change is f of a plus h minus f of a. And so this is the change in y, which is delta f sub a at h. It is f of a plus h minus f of a. So this is my delta f sub a at h. So that's this whole distance here, this whole quantity here. This is my h. So this is my h. This here. Next, this here is df sub a at h equaling h times f prime. Why? Let's look at some similar triangles. Well, let's say that this is equal. I'll show you why that is in a second using similar triangles. So this is delta f sub a at h. This is d sub df sub a at h. Therefore, this is the difference of those two. Delta f sub a at h minus d sub a at h. And we are saying that this is little o of h. And so this says that, can I find some linear transformation so that this difference here is little o of h? Can I find some linear transformation so that this difference here is little o of h? Okay, so let me look at some similar triangles. So this is h here, and this is, well, don't know yet, and we'll figure it out. But what is f prime at a? Well, it is the slope of the tangent line at x equal a. So if I go out, what's a slope mean? That means if I go one distance here, then this distance, then this here is my my slope. And so, now of course, if it's positive, you go up, and it's negative, you go down. And so I have the following right triangle. So I have a 1 f prime. If this is h, well, and if these are similar triangles, which they are, then this must be h times f prime at a. And so the limit as h approaches 0 of delta f sub a at h minus df sub a at h divided by h is equal to, well, this is just that. The limit as h approaches 0 of, and this is my delta y. So this is equal to the limit as h approaches 0, f of a plus h minus f of a minus h f prime at a divided by h, which I can say by the properties of the limit is just this limit minus this limit. but the h's cancel here. So this is the limit as h approaches 0 of f of a plus h minus f of a over h minus this guy. These cancel, and you take in the limit as h approaches 0 of a constant. So it's just equal to that constant. But if this is 0, because, well, I'm assuming that the derivative, that the function f is differentiable at a. Therefore, these are the same, and so this is equal to 0. And so this is equal to 0. Therefore, the numerator, delta f sub a at h minus d f sub a at h is equal to little o of h. Therefore, delta f sub a at h is equal to d f sub a at h plus little o of h. So let me delve in a little bit more into the idea of what is this linear transformation. So first off, I guess I have to tell you, well, a linear transformation is a function between vector spaces. So I have to tell you what a vector space is. So let's recall what that a vector space is a set consisting of vectors and of scalars. Scalars are just numbers in some sort of scalar field. So let me remind you what a field is. A field is, well, if you remember back in Math 115, Algebra 1, a field is something that, a set that has addition on multiplication on it, that satisfies the properties that the rational numbers satisfy. And so, the field properties. Let F be a set with binary operators plus and addition and multiplication, meaning that addition takes two numbers and gives me another number, meaning that addition is a function from the Cartesian product of f with itself to, so f Cartesian product with f to f. So it's a function from the Cartesian product of f with itself into itself. Same for multiplication. It's a binary operator. Negation, taking the additive inverse, is a unary operator. It takes functions from your field and gives you another member of your field. Similarly, multiplicative inverse. Oops. Your multiplicative inverse is a unary operator. It takes some member in your field and gives you another member in your field, so long as you're not trying to do it to zero, so long as it's not zero. So any non-zero member of your field to some non-zero member of your field. 0 and 1, well, 0 is the additive identity, and 1 here is the additive, is a multiplicative identity. These are both nullary operators. They just give you, no matter what, a member of your field, a particular member of your field. So let me write down the field properties. So for every A in your field, in your set F, for every B in your set F, and for every C in your set F. I have the closure property for addition. A plus B is a member of F. If you take two numbers and you add them together, you still get a number. The closure property for multiplication. If you multiply two numbers together, you still get a number. Next, the associative property for addition. A plus the quantity B plus C is equal to A plus B plus C. Next, the commutative property for the associative property for multiplication. And so the associative property for multiplication says that A times the quantity B times C is the same as A times B times the quantity C. The commutative property for addition, A plus B is equal to B plus A. The commutative property for multiplication, A times B is equal to B times A. The existence of an additive identity. There exists some additive identity, and we'll denote the additive identity by 0, such that for every number A plus 0 is equal to A. And similarly, well, actually, so that makes this a right additive identity. But by the commutativity, 0 plus A is also equal to A. And so it's also a left additive identity. So we just call it additive identity. There also exists a multiplicative identity. So there exists a multiplicative identity. We'll denote the multiplicative identity by 1. So there exists a multiplicative identity such that for every number A times the multiplicative identity, we get back the original number A. And so this is a right multiplicative identity, but by commutativity for multiplication, 1 times A is also equal to A. So it's also a left multiplicative identity. And so it's a, since it's both a right and left sided identity, we can just call it a identity, multiplicative identity. Let me assume that that 0 is not equal to 1, just so that our field involves more than one number. We can also do that by specifying this, but so we sort of specified it here. For every number A in our field, there exists, well, its additive inverse, denoted by minus A. So for every number A, there exists a additive inverse, negative A, such that A plus its additive inverse is the additive identity. And so this is a right additive inverse. By commutativity of addition, it's also a left additive inverse. For all non-zero numbers, there exists a multiplicative inverse denoted by A with this little superscript of -1, so that a number times its multiplicative inverse is equal to the multiplicative identity. And so this is a right multiplicative inverse. And we will assume that, and since multiplication is commutative, this will also be a left multiplicative inverse. And we have that multiplication distributes over addition. So A times the quantity B plus C is equal to A times B plus A times C. So let's talk about a vector space. A vector is a member of a vector space. A scalar is a member of its scalar field. And so, let me give you some vector space properties. Let V be a set with the following properties. So there's a binary operator of addition. There is scalar multiplication. Scalar multiplication takes a member of your field, Cartesian product with a member of your vector space, and gives you a member of your vector space. And so a scalar multiple, a number times a vector gives you a vector. Okay. So I have some set of vectors, V. I'm able to define a binary operation, addition of vectors, scalar multiplication on the field Cartesian product with the vectors, a additive identity for the vectors for vector addition, and a additive inverse for my vector addition. So, and we have a field, just like what we had from before. So let U, V, and W be members of the set V vectors, and let C and F be members of your field, your scalar field. So let let C and D be numbers, scalars. Let U, V, and W be vectors. Then I have that the closure property for vector addition. A vector plus a vector is still a vector. So if U and V are members of your vector space V, then U plus V is also a member of your vector space V. Next, I have that vector addition is commutative. And so U plus V is equal to V plus U. And vector addition is associative. U plus the quantity V plus W is equal to U plus V plus W. We have the existence of a additive identity for addition for vector addition. And so I have the zero vector. There exists 0 in the set V such that the additive identity plus U, well, U plus the additive identity is the original vector U. And so I have that this is a right additive identity, and by commutativity, it's also left additive identity. So it's just an additive identity. There exists an additive inverse, so that any vector plus its additive inverse is the additive identity. And again, it'll both be a right and left additive inverse because of commutativity for vector addition. Scalar multiplication. So now let's do some properties for scalar multiplication. So if C is any scalar and U is any vector, then a scalar multiple of any vector is still a vector. Scalar multiplication distributes over vector addition. So let U and V be vectors and C be some number. Then C times the quantity U plus V is, well, CU plus CV. I have that scalar multiplication distributes over scalar addition. So I have here scalar addition. I have two numbers, and I'm adding them together. Then C plus DU is equal to CU plus DU. Next, we have that if C and D are scalars, then C times D, scalar multiplying, times U is equal to C, scalar multiplying, and scalar multiple DU. And lastly, the multiplicative identity for your scalars is the scalar multiple identity. So 1 scalar multiplying some vector U is just the vector U. So now I can define what a linear transformation is. So I gave you a intuitive idea, more or less, of what a linear transformation is. Let me be a little bit more specific. So let U and V be vector spaces over field F, and let L map V into W, be a function, such that for every number R in your field F, S in your field F, U in your vector space V, V in your vector space V, we have that L at RU plus SV is equal to RLU plus SLV. If this happens, then L is called a linear transformation from L into W. VW. There are many. So this is one sort of definition for what of VW is. In mathematics, it's actually used for several different concepts. This is one of the major concepts that it's used for, but not the only one. So HOM at VW is the set of all the set of all L such that, well, it's a set of all linear transformation. It's a set of all L such that L maps V into W is a linear transformation. So this just stands for the set of all linear transformations from V into W. So sometimes we use that because we're lazy and we don't want to write this whole phrase down. And we just say, well, that L be a member of this set. The little o and big O notation. So we've seen this before. Well, we've seen the low. So let me tell you little o and big O. That F map V into W. Then F is big O if F evaluated 0 is 0, and if there exists a neighborhood of 0 and some constant C greater than 0, such that for all X in the neighborhood of 0, the length of f of x, the norm of f of x, is less than or equal to C times the norm of V. Now, f of x is in the maps of v into w. So this norm, this length here, is a length in w. And x is, well, a member of v. So this length here is your length, your norm in v. You may have differing lengths in differing vector spaces. So that's why we have a subscript. For right now, we'll only talk about really one way of finding a length, just taking the difference of two numbers and taking their absolute value. Taking the absolute value of a particular number gives you a length of that number. We say that f is Lipschitz continuous at 0 if we have the following. Oh, I'm sorry. There it is right there. If we have this here. Such a function is called big O, and we denote it as f being big O as follows. F is a member of big O of LW. So if this happens, if f satisfies this, then we say that we denote it by it's in that is big O of VW. So f is little o if f of 0 is 0 and the limit as x approaches 0 of the norm of f with respect to the w norm divided by the v norm of x is 0. Such a function is called little o, and it's denoted by when we say that f is a member of little o of VW. Let me give you some examples. If f of x is equal to x, then f is big O. Because, well, obviously f of 0 is 0, and the norm of x is less than or equal to 1 times the norm of x. But it's not little o. If you divide the norm of x by the norm of x, you don't get 0, you get 1. And so it's big O, but it's not little o. Next. So that means that big O is not the same as little o. It turns out that little o is, that big O is a subset of little o, but okay, so if anything is little o, then it's going to be big O. If f of x is equal to x to the 3/2, then f is both big O and little o. If you look here, well, the norm of x to the 3/2 divided by x. Well, if you divide x to the 3/2 by x, you get x to the 1/2. So as x goes to 0, well, x to the 1/2 still goes to 0. And so it's a little low. And certainly if it's little o, you can make this bound. So it's also big O. So it's both big and little o. So note that little o of VW is a subset of big O of VW. And VW is a subset of big O of VW. So again, we usually write f of x equals big O of x if f is big O, and we write f of x equals little o of x if f is little o. So let me give you slightly more precise definition of the derivative. Let V and W be normed vector spaces, and let N sub A be a neighborhood of A in V. F mapping the neighborhood of A into W is differentiable at A if there exists df sub A in Hom VW, meaning there exists a linear transformation df sub A from the vector space V into the vector space W, such that delta F sub A at H is equal to df sub A at H plus little o of H. df sub A is called the differential of F at A. It is the unique bounded linear transformation to delta F sub A. The Frechet differential. Let V and W be normed vector spaces. Let N sub A be a neighborhood of A in the vector space V. Then F mapping the neighborhood of A into the vector space W is differentiable at A if there exists a linear transformation df sub A from the vector space V into the vector space W, such that the limit as H approaches 0 of delta F at H, delta F sub A at H minus df sub A at H, divided by the norm of H, the V norm of H, is equal to 0, which is actually the additive identity for the vector space W. In the case that V and W are the real number line, the case that we're looking here in Map 261, the matrix representation of df sub A is called the derivative of F at A. In this case, we have that the limit as H approaches 0 of, I didn't need to. You can just write one line. Usually when we do it in R, we don't put two lines here, but one line, meaning it's the absolute value. So F of A plus H, the limit as H approaches 0. F of A plus H minus F of A minus F sub A at H in absolute value divided by H in absolute value is 0, where df sub A at H is F prime at A times H. So let's do some examples. On page 127, let me do problems 19 through 29. Find the derivative of F of the function, sorry. Find the derivative of the function. Oops. Find the derivative of the function using the definition of derivative. State the domain of the function and the domain of the derivative. And so we have here problem number 22. F of x is equal to 4 plus 8x minus 5x squared. Okay, so let's find the derivative using definition of the, find the derivative using definition of derivative. I will use the definition of derivative that I have just given you. So let's do this. Let's note that a function is differentiable if we have the following. And this is for all points. So maybe I'll call it x. So delta f sub x at h is equal to df sub x at h plus little o at h. So if there exists, maybe I should actually, oops. Let me bring that down. Okay. I guess I can't bring that down. Okay. So f is differentiable at x if there exists a linear transformation df sub x h such that delta f sub h equals df sub x at h plus little o at h. There. And so let's figure out what each of these are. Delta f sub x at h is equal to, well, by definition, f x plus h minus f of x. And d f sub x at h is a linear transformation from, well, oops, from R to R. Okay. And well, it's a linear transformation from R into R. So that means that there's some sort of matrix. I'll give a matrix representation for this linear transformation. And so df x at h is equal to some matrix times h. So where A is the matrix transformation, matrix representation of the linear transformation but this matrix, since this is going from R to R, the matrix representation, there's a one-to-one correspondence between this matrix. It's a one-by-one matrix and a real number. And so let f prime at x denote the real number so this real number is, well, going to be the correspondence to this matrix. So there's a isomorphic representation. So isomorphism. For the matrix A. So that says that df sub x at h is just a number times h. So it's just some number times h. Okay, good. So now let's see what this says. So if I retranslate each of these, so this is that, and this is that. Okay, so now I have that delta f of x plus h minus f of x is equal to some number f prime of x times h plus a little o of h. So I want to see if, so I want to find this f. So here in problems 19 through 29, find the derivative of the function using the definition of the derivative, state the domain of the function and the domain of the derivative. So problem number 22, f of x is equal to 4 plus 8x minus 5x squared. So first off, let's recall what it means to be differentiable. And I will use this particular definition of differentiability. I'll use other definitions of differentiability in differing problems, but I'll use this definition in this problem. F is differentiable at x if there exists a linear transformation d f sub x at h such that delta f sub x at h is equal to df sub x at h plus little o of h, where delta f sub x at h is equal to f of x plus h minus f of x, and df sub x at h is a linear transformation from the reals to the reals. Since we're going from, we have a linear transformation from the reals to the reals, then excuse me, then the linear transformation df sub x at h is equal to D is equal to some matrix A. And actually this matrix A will depend on X. So maybe I'll put a subscript here of X. Okay. So where A sub x is the matrix representation of the linear transformation df sub x, where f prime denotes the real number isomorphism for the matrix, A sub x. And so this matrix A sub x is just a very small matrix. It's just a matrix consisting of one number. And so it's some number, which I'll denote by f prime, and it is a function of x. So this matrix is just, the number 3. It's just one number. And so I will represent this as, well, just the number. And so we can represent the linear transformation df sub x at h as f prime at x times h. So what we want to do, so now I can translate this statement into our particular situation. Well, this delta is just equal to y2 minus y1. This linear transformation df sub x at h is just the number f prime at x times h, and plus this little o. So what this says is that I want to somehow find a number so that this, so that this is equal to this. And so somehow I want to manipulate this so that I can find, so I want to just take this for my particular situation here and see if somehow I can get some number times h plus some other things. If I can do that, then I'll be very happy, because then in that particular situation, I'll be done, because that's what I wanted to determine. Okay, so let's do this in this particular situation. And so I have here that f of x, so maybe I should say where f of x is equal to 4 plus 8x minus 5x squared. Okay, so let's do that for that particular situation. So f of x plus h is equal to, so let's, in this particular situation, replace replace every x in the formula for f by x plus h. Simplify and then see what happens. Okay, so let's do that. So wherever I see an x here, I'm going to replace x by x plus h. So I'm going to replace each of these x's by x plus h. So this is 4 plus 8 x plus h minus 5 x plus h squared. And so now let me simplify that. And so this is equal to 4 plus, let me multiply 8 inside the parentheses. Okay, and so this is equal to 8x plus 8h minus 5 times. Now let me use the special product formula to simplify the x plus h quantity squared. Let's use the perfect square trinomial formula. And so this is equal to x squared plus 2xh plus h squared. And let me multiply negative 5 inside the parentheses. So this is equal to 4 plus 8x plus 8h minus 5x squared, oops, minus 10xh minus 5h squared. Okay, now let me look at f of x plus h minus f of x. So it's just going to equal this minus this. So 4 plus 8x plus 8h minus 5x squared minus 10h minus 10xh minus 5h squared minus, well, f of x, which is 4 plus 8x minus 5x squared. So this is equal to, let's get rid of all the parentheses. So if I do that, this is 4 plus 8x plus 8h minus 5x squared minus 10xh minus 5h squared. Let me distribute the minus sign inside the parentheses. Minus 4 minus 8x plus 5x squared. I could do some cancellation. 4 cancels. 8x cancels. 5x squares cancel. And so I get a negative, let's write this first, negative 5h squared so that's this term. Then I have this term, so minus 10xh. And lastly, I have this term. So plus 8h. Let's factor out h. So I get here h. Actually, let's do this. Let me write it this way. So let me write the minus 10x h plus 8h together and the minus 5h squared. Why? Because let me factor out h, and maybe I should put parentheses around this. Let me factor out h from this first grouping. So this is h. Oh, and let's actually write it this way. Minus 10x plus 8 all times h minus 5h squared. And note the following. And so limit as h approaches 0 of negative 5h squared over h well, the h's cancel. One of the h's cancel. So this is just equal to the limit as h approaches 0 of a negative 5h, which is 0. Therefore, negative 5h squared is little o of h. And so I have that f of x plus h minus f of x is equal to, well, negative 10 x plus 8 h plus little o of h. Oh, and if you look, I wanted to rewrite this as some function of x times h, no h's here, plus little o of h. Some function of x, no h's, times h, plus my little o of h. Therefore, this is my derivative. I found, so this is, well, maybe I should write in red. So this is my df sub x. Here is my h. And this is my little o of h. And so I have here that the derivative that this is minus 10x plus 8h. And so I have that the derivative is negative 10x plus 8. And that's what I wanted to find. Now, only thing is I didn't tell you the domain. Well, what's the domain? The domain of f, well, that's pretty easy. Here's my function, it's a polynomial. The domain of a polynomial is all real numbers. And what's the domain of f prime? Well, that's a line. So the domain of a line is all real numbers. So the domain of my original function is all real numbers, and the domain of my derivative function is also all real numbers. Any questions about this? So it turns out that what you're doing is you are somehow finding an approximation to this difference. So I looked at this difference and I tried to somehow see if there was some way I could approximate it to first order. So this is the first order term in H of this difference. And we call that first order difference, the derivative. Okay, so let's do the next problem. Problem number 24. G of t is equal to 1 over the square root of t. So let me use a different definition of the derivative to do this. So the difference quotient. A definition of derivative. Now, this difference quotient definition of derivative is really only applicable in this course. You can't really use it for, say, calculus 3 or whatever, because it really is not applicable. But it is for this course. So let me use this definition. So G prime at t, let's say, is equal to the limit as h approaches 0 of g of t plus h minus g of t, all divided by h. So let's look at this particular situation for g. When g of t is equal to 1 over the square root of t. Well, to evaluate g of t plus h, wherever I see a t in the formula for g, I replace t by t plus h. So let's just replace this t here by t plus h. And so I get 1 over square root t plus h minus, well, g of t is just, well, 1 over the square root of t. All divided by h. Let me try to simplify this. So if you plug in 0 for h, well, so if this is 0, then this is just equal to 1 over the square root of t minus 1 over the square root of t is 0 over h, which is 0. 0 over 0 means do more work. So first, I don't like denominators. So let me get rid of the denominators. To get rid of the denominators, I'll just multiply by, well, the denominators. Let's multiply the numerator by the square root of t plus h times the square root of t. And do the same thing in the denominator. Maybe I'll write the t first and then the t plus h. So let's multiply and divide by the square root of t plus h times the square root of t. Well, the square root of t plus h's will cancel. So you're just going to get the square root of t. square root of t's cancel. So all that you get here is the square root of t plus h. And well, for your denominator, you get that huge product. So h radical t plus h. Now, all nice and fine. Still, notice again, if you plug in h equals 0, you get, well, square root of t minus the square root of t, 0 over 0. So do more work. So again, we have to still do more work. Well, in this case, I want to get rid of the square roots. And so I'll multiply and divide by the conjugate of the numerator. And so let's do that. And so I have here the square root of t plus the square root of t plus h, the conjugate of the numerator. And let's divide by the same thing, the square root of t, square root of t plus h. Okay, so this is just going to be the limit. As h goes to 0 of, well, this is now, since I'm multiplying by the conjugate, then each of these square roots will disappear. And so this is equal to t minus t plus h in the numerator. And in the denominator, well, it's just going to be this product here. And so divided by h radical t plus h times the quantity radical t plus h plus radical t. Yeah. And so let me get rid of the parentheses in the numerator. So this is equal to limit as h approaches 0 of t minus, actually I should change all the signs. So minus t minus h divided by, well, the same thing, that huge denominator. H radical t plus h times the quantity radical t plus h plus radical t. The t's cancel. And so I get limit h approaches 0 of negative h over h radical t plus h radical t plus h radical t. H's cancel. And so I get limit as h approaches 0 of negative 1 over radical t radical t plus h radical t plus h plus radical t. Okay, so now let's, well, plug in h equals 0. And so if I do that, well, the numerator is still negative 1. Radical t is still radical t. Radical t plus h becomes radical t. Radical t plus h becomes radical t. And radical t remains radical t. So I get -1 over radical t, radical t, radical t, plus radical t. So there are two of these radical t's, and there's going to be 3 radicals. So this is t to the 3/2, which sometimes we write, well, maybe I'll leave it like that. And so that's your answer. That's the derivative. So let's find the domain. And maybe I'll write it here. So this is equal to -1 over 2 t to the 3/2. So let's find the domain of G. Well, let's look back at G. If I look at G here, it's 1 over the square root of t. You don't want to divide by 0, so t is not 0. You also don't want to take the square root of a negative number. So t is neither negative nor 0. T is positive. And so the domain of G is just positive numbers. So the domain of G is 0 to infinity. The domain of G prime, well, it's the same situation. So I have the same situation as before. I don't want to divide by 0. I don't want to take square roots of negative numbers. And so the domain is 0 to infinity. And as before, we noted that the domain is a of the derivative is a subset of the domain of the original function. Any questions about this? And so that's my derivative. Let's look at problem number 26. Okay, so for problem 26, let's use, again, the difference quotient definition. Of the derivative. So the derivative is the limit as h approaches 0, f of x plus h minus f of x all divided by h. So this is equal to limit as h approaches 0 of, well, again, wherever I see an x in the formula for f, replace x by x plus h. So x plus h squared minus 1 over 2 x plus h minus 3. So again, wherever I see an x, I'm replacing x by x plus h minus f of x, which is x squared minus 1 over 2x plus minus 3, all divided by h. And now let me simplify this. So I guess in this case, I want to get rid of denominators. So let me multiply and divide by the common denominator. And so I have here a 2x plus h minus 3 times 2x minus 3. So I'm going to multiply and divide by this. Okay, so this is equal to limit as h approaches 0 of, well, the 2x plus h minus 3's cancel. So you're just going to multiply this times this. Well, first let me square this out just to make life a little easier. Well, eventually to make life easier, not originally. And so this is x squared plus 2xh plus h squared minus 1. Oh, let's just times my 2x minus 3 minus, well, the 2x minus 3's cancel. So what remains is this times that. Let me multiply the 2 inside. And so I have here x squared minus 1. Oops. X squared minus 1 times 2x plus 2h minus 3, all divided by h times 2x plus h minus 3 times 2x minus 3. So this is equal to limit as h approaches 0 of I guess let's multiply this out. Okay, so I'm gonna have to multiply this out. So this is let's multiply each of these by 2x. And then I'll multiply each of these by minus 3. So I get 2x cubed plus 4x squared h plus 2xh squared minus 2x. So all I've done here is I've multiplied each by 2x. Okay. Now let's multiply each of these by minus 3. Okay. So minus 3x squared. Oh, good grief. Minus 6xh minus How in the world am I going to fit this? Okay, let's do the following. Let's move this over. Okay. This is going to be big. Okay, so minus 6xh minus 3h squared plus 3. Okay. Oops. Okay. I'm going to try to get as much room as I can because this is big. Okay. Let's see if I can fit it. Okay, so now multiply each of these by a negative x squared. So negative 2x cubed minus 2 x squared h plus 3x squared. How in the world am I going to do this? Okay. Okay, so let's try that. So I need even more space here. Okay, so it's really big. Minus these. So now I'm going to be multiplying a minus and a minus 1. So that's plus 1 times this. So just plus this last term. So let's see if I can fit this in. Plus 2x, 2h. Oof, just barely. Minus 3. Okay, so this now it's going to, I'm going to have cancellations. So it's not going to nearly be, it's big. Okay, hopefully I can cancel several terms here. So it won't be nearly as long. 2x cubed. Minus 2x. Minus 3x squared. And then the 3. Where's the 2h? Okay, so 1, 2, 3, 8 terms. Okay, so this is equal to I should be able to fit everything now. 4x squared h minus 2x squared h is 2x squared h okay. I guess that's it. All the other ones. So this is x h squared. Okay, so let's look at the other h terms. So I have this h term, and that's it. So, and then this h term. So let's write those other two down. So minus 6xh plus 2h. So those are all the terms involving h. Let's see the terms involving h squared. There's only one term involved, two terms involving h squared. So plus 2x h squared minus 3x h squared. I think that's it. Let me just check. And that looks correct. Oh, except my denominator is completely wrong. Going from one end to the other end. My denominator is wrong. It's not just h. There's a whole bunch of other terms in here. So let me write my denominator correctly. Times, and let me multiply the 2 inside the parentheses. So 2x plus 2h minus 3, 2x minus 3. So this is equal to, oops, h, 2x plus 2h minus 3, 2x minus 3. And I can factor out actually a h from the numerator. So let me do that. This is equal to the limit as h approaches 0 of h 2x squared minus 6x plus 2 plus 2xh minus 3h over h 2x plus 2h minus 3, 2x minus 3. Okay, I can cancel the h's. So this is equal to limit as h approaches 0 of 2x squared minus 6x plus 2 plus 2xh minus 3h over 2x plus 2h, oops, minus 3, 2x minus 3. Now, let me plug in 0. So if I plug in 0 for h, I'm going to just get 2x squared minus, so these terms will vanish, and this will vanish, but all the other terms will remain. So these will remain, these, and these. And so I have that this is equal to 2x squared minus 6x plus 2 over 2x minus 3 times another 2x minus 3. And so this is equal to I can factor out a 2, but I don't need to. This will equal 2x squared minus 6x minus 2. So, plus 2. So 2x squared minus 6x plus 2 divided by 2x minus 3 squared. And so that's my derivative. So my derivative has the form 2x squared minus 6x plus 2 divided by 2x minus 3. Note that the domain, my original, maybe I should even write it this way. So therefore f prime is equal to 2x squared minus 6x plus 2 over 2x minus 3 squared. So the domain of f, well, if you look here, it's a rational function. So the only bad thing is when you divide by 0, when 2x minus 3 is 0, when x is 3/2. So it's everything except when x is 3/2. And as far as the derivative, it's another rational function. So again, you don't want to divide by 0. So the domain of f prime is again the set of all x's not equal to 3/2. And so just like before, we have that the domain of f prime is subset of the domain of f. Any questions about this? Any questions on this? Unfortunately, it's a lot of algebra. So a lot of algebra in this. Nothing difficult other than, so many places to make an error. So there's just, almost an infinite number of places to make an error in this computation. All I can say is don't make errors. It's very long and tedious, but just try not to make an error in the calculation, in these long calculations. So nothing difficult, just involves so many places where you can make a small error. So let's find the derivative of problem 28, x to the 3/2. So again, let's use the difference quotient definition. And so the derivative is equal to limit, as h approaches 0, f of x plus h minus f of x over h. This one will not involve nearly the amount of algebraic computations as the last one. And so this is a limit as h approaches 0 of, well, wherever I see an x in the formula for f, replace x by x plus h. So I'm just going to plug in x plus h here. So this is equal to x plus h to 3/2 minus x to 3/2 all divided by h. Let me get rid of the square roots. And so let me multiply and divide by the conjugate of the numerator. So let's multiply by x plus h to the 3/2 plus x to the 3/2, all divided by x plus h to 3/2 plus x to 3/2. So this is equal to limit as h approaches 0 of Well, I have the product of the sum and difference of two terms. Therefore, it's the difference of squares. Well, the square gets rid of the 2 in the denominator. So this is just x plus h cubed minus x cubed, all divided by, well, the denominator. The x plus h to 3/2 plus x to 3/2. So this is equal to, well, let's cube this out. And so if I cube using the special product formula, the perfect cube formula, we get that this is the limit as h approaches 0 of x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed over h, x plus h to 3/2 plus x to 3/2. Oops. So this is equal to the limit as h approaches 0 of, well, the x cubes cancel. So 3x squared h plus 3x h squared plus h cubed all over h, x plus h to 3/2 plus x to 3/2. And so let me factor out an h in the numerator. So this is equal to limit as h approaches 0 of h 3x squared plus 3x h plus h squared over h, x plus h to 3/2 plus x to 3/2. H's cancel. So this is the limit as h approaches 0 of 3x squared plus 3x h plus h squared over x plus h 3/2 plus x to 3/2. Let h go to 0. So if I let h go to 0, well, this term, these two terms disappear, and so does this term. And so what I have remaining is 3x squared in the numerator and x to 3/2 plus another x to 3/2 in the denominator. And so this is 3x squared over, well, there's two of these, x to 3/2. And so this is equal to, well, 2. So I have a common base of x. I'm dividing, so I subtract numerators. 2 minus 3/2 is 1/2. So this is 3x to the 1/2 over 2. So this is equal to 3/2 radical x. And that's your answer. That's your derivative. Actually, maybe I should say that that's my derivative. So my derivative is 3/2 radical x. And so let's try to find the domain of f. Well, let's see. Oh, here. don't want to take the square root of negative numbers. So I don't want to take the square root of a negative number. Therefore, I want that my x's are non-negative. Let's look at the domain of f prime. Well, again, you don't want to take the square root of a negative number. And if at this left endpoint, I take my right derivatives, so the domain is, well, in this case, oops, 0 to infinity for a two-sided derivative. But if I allow the domain if I allow this, and I usually do, where in this case, you have to use the right derivative. Of f at x equals 0. So the right derivative of f at 0 is defined, not the left derivative, but the right derivative. So if I use that sort of specification that when I include 0, I can just look at the right derivative. Then the domain is this. But unless you tell people you're doing this, this is your domain. So your domain of your derivative, meaning the two-sided derivative, is 0